Welcome back. As promised, at the end of the first part of this course session, what we are going to look at now in more detail is this notion of transformation from n tuples to m tuples of real numbers, from vectors to vectors of appropriate dimension. So let's connect with what we were doing before, just to show you somehow pictorially what is it that these transformations actually mean. People love pictures for some form or another. I'm more of an algebraic guy myself, and that's because unfortunately I didn't inherit Michelangelo's drawing skills. So remember, we looked at this transformation here that goes from pairs of real numbers to pairs of real numbers, and this transformation takes a vector xy and it doubles the x component and leaves the y component unchanged. So t of xy should be t2, since I call that map t2. t2 of xy goes to 2xy. So what does this mean? So let's look at our xy plane, at our Cartesian plane, named after René Descartes, who introduced it to us. So what happens? Okay, so suppose that we take the point 0, 0, the point 0, 1, 1, 0, and the point 1, 1. That's before we apply the cure, that is the transformation T2, to our little square. So let's consider the square, which is spanned by these 4 points in the plane. So what happens to this square when we apply the transformation T2? In case anybody asks what this curly arrow labeled T2 means, I say, okay, let's apply the transformation T2 and see what happens. And let's change color. Let's make it blue. So what happens to the point 0, 0? Where does it go? It stays where it is, because we're not going to need any of these, but let's pretend we do. Okay, so what happens to this, the point 1, 0? Where does it go? It goes to 2, 0. It goes here. And in case you want, sort of, well, this goes to this one. This goes to this one. So what happens to the point 0, 1? It stays the same, because 2 times 0 is 0, so it stays where it is. So this goes where it was. Okay? So what happens to the point 1, 1? It goes, as we computed before, to 2, 1, so it goes here. So what is it that we've done? So that we have doubled the original square spanned by these 4 points, and it's become a rectangle, because we have expanded by 2. We have expanded by 2 the x component, and we've left the y component unchanged. This is a kind of map which is called the x expansion, because we are multiplying the x component by some factor which is greater than 1. We could also multiply the x component by a factor which is between 0 and 1, and in that case what we get is a shrinking. So we take x, we put him on a diet, and out comes the new x, which could be half of the original x, before x eats again, and then it will pick up even more weight than it had lost. That's what diets are for. Okay, so this is an expansion. And you can imagine that this kind of stuff is actually useful when we draw things. For instance, if you wanted actually to take your original square and out of it build a square whose sides are 2 times bigger than the original one, then what do you think you would need to do? Your colleagues in the room are saying, well, you will multiply both x and y by the same factor 2. So in that case, the map would be a map which is defined as follows. Give me an x, give me a y, I'll give you a 2x, 2y. So this is not only an x expansion, but it's also a y expansion by the same factor. Beautiful. Let me give you some other example. And let's do it on a new page. Actually, not on a new page, because I had it cooked before. So here you are. Here's our xy plane. And here are some points which, sorry, are some kind of a very rough approximation of a smiley, even though the thing is not really smiling. It's this, there are the 2 eyes, and the dots there are just, well, they're the mouth. Okay, suppose that I want to take a mirror reflection on the x-axis. So what I would like to do is to take this picture and turn it into this. Okay, so this is like in Snow White, when the beautiful but wicked princess or queen just looks at herself in the mirror and asks, who's the most beautiful of the realm? The blue one or the green one? Well, it's the same, because one is the X reflection of the other. Now, you know what I'm about to ask you, is what kind of transformation should I apply in order to turn the blue dots into the green dots? So let's see. This is a transformation that takes a point xy and maps it to what? Well, the x coordinate does not change. But one of your colleagues, I overheard, one of your colleagues said, okay, I'm supposed to map a point that has y coordinate 1 to one which is y coordinate -1. I'm supposed to map a point which is y coordinate 2 to one that is to a green one which has y coordinate -2. So how about this? Give me an x, I leave it unchanged. Give me a y, I'll negate it. I take the -y. Well, that's called a reflection. Oh, not reflection. That's something that's got to eating. It's got to do with eating, reflection. But we are going to do something related to mirrors, namely reflection on the x-axis. That's something that you can achieve, for instance, in computer graphics, by means of a matrix transform, by means of a transformation. Later on, we will see that it's indeed something which is induced by a matrix, but that was my punchline later on. I sort of revealed it now. I revealed the killer. It's the butler, and he did it for money. It's always like this, isn't it? Okay, so do you want to see another transformation? Let's do another transformation, then we will move on, because I cannot do examples forever. But examples are cool. So let's do another one. Let's do a transformation which people call an X shear. Wow, what does this mean? Okay, so we take xy and we map it to x plus ay, so let me call it t sub a, where a is the factor that we are using to do something to our points, to something like this. So let's see what this does to a picture. And since I'm drawing, I'll keep the picture simple. Okay, so let's get these 4 points here that span our beautiful square with unit side. Okay, so let's assume that our shearing factor A is, I don't know, let's say it's 2. Let's see what happens. 1, 2, 3, 4, not that we need it, but there you are. 1, 2. So where does the point 0, 0 go? It goes to 0, 0. Why? Because, okay, so that we are supposed, absolutely, multiplication with 0 is 0. So we are supposed to take xy to what? To x plus 2 times y, y. So if x and y are 0, then we get 0, 0 out. What happens to the point 0, 1? Where does this go? It goes to, okay, sort of 0, 2 times 1, it goes to 2, so it's 2, 1. So it goes here. What happens to the point 1, 0? Okay, 1, 0, it goes to 1 plus 2 times 0. So that's 1, 1. Is that right? No, sorry, 1, 0. Oops. So it goes to, what did I say? 1, 0, it goes to, I'm confused now. Forgive me. No, sort of 1, 0, it goes to 1 plus 2 times 0 and 0, isn't it? So it goes to 1, 0. Okay, so what happens instead to the point 1, 1? It goes to 3, 1. So what we've done is we've taken our square and we have tilted it by this factor here. The tilt is towards the right because the factor that we've used for tilting is the shearing factor is positive. If it was negative, we would just have tilted the other way. So if instead of 2, you would have taken -2, now the figure would look something like this. So this would be sort of like a -2, x minus 2y, x. This would be the transformation. That's sort of y, not x. Okay, that's another example of a transformation. You take your picture in the 2-dimensional plane, and by applying a function, you tilt it in one direction. And how much you tilt it depends on the multiplying factor A. That's another thing that people do when they apply transformations in computer graphics. These are, of course, very simple transformations, but the important thing is that they can all be achieved by means of applying a function. So you could actually write a function, which is what people do, to implement these things. Now, what do these functions have to do with matrices? Let's see. We will see right now that these functions have a lot to do with matrices. Let's define, first of all, a kind of transformation which is induced by a matrix. So if we take a matrix with m rows and n columns, this matrix actually can be used to define a function from n tuples of natural numbers, of real numbers, to m tuples of real numbers. This function is defined using matrix multiplication. So what is this function? It says, give me a vector x, I'll multiply it by a, and the result is what I spit out. Now, this vector x should be of the appropriate size. Since the matrix A has n columns, this vector x should have n components. So it should be a vector in Rn. But when you multiply it by this matrix, you get a vector with m rows. That's why this is a function from Rn to Rn. From the dimension of the number of columns in the matrix to the dimension of the number of rows. So let me ask you, before we saw the identity transformation, give me a vector, I spit it out unchanged. Okay, so can you think of a matrix that implements this operation? This is not a trick question, and I can say, what's in a name? The transformation is called the identity transformation. So what kind of matrix actually would induce the identity transformation? The identity matrix. Why? Because this matrix says, okay, multiply me with something, I'll give you the thing you multiply me with. That's what the identity function does. Give me an argument, I'll spit it out unchanged. We saw another basic transformation, namely the zero transformation. Give me an argument, I'll spit out the zero vector. Do you think there is a matrix that actually implements this operation using this transformation using matrix multiplication? Hello? I can hear the people at home saying, okay, what's in a name? This was called the zero transformation. So the matrix with all zeros in it, the zero matrix of the appropriate size, will just return zero no matter what you multiply it with. Just like any number multiplied by zero is zero. Any vector multiplied with the zero matrix of the appropriate size is going to return the zero vector. So let's look at some more interesting transformations, shall we? For instance, the ones we were looking at before. So let's look at this one. Reflection on the axis. Do you think this transformation is a matrix transformation? In other words, is there a matrix A, a 2x2 matrix, such that A times xy is going to be x minus y? Is there such a matrix? What do you think? Your colleagues here in the room are saying yes, and the yes was so resounding that it reverberates still through the room. And I can even hear you at home saying yes. So what matrix is this? Oh yeah, one of our colleagues is saying the empty matrix. Well, at the moment it's empty, but there are going to be 4. This is going to be a 2x2 matrix. The reason why it's empty is because I would like you to figure out what should be there. Okay, let me give you a trick, which is actually more than a trick. Later on, we will see that that's the way to construct the matrix from a function that can be represented using a matrix as a matrix transformation. Okay? You look at the 2 columns of the identity matrix of size 2. The first column says 1, 0. What happens when we apply the transformation, which is the reflection on the x-axis, to 1, 0? Nothing. We get 1, 0 back. What happens if we apply the transformation to the other column, 0, 1? It becomes 0 minus 1. Okay, that's a matrix. Let's see whether it does the job that we designed it to do. What is 1, 0, 0 minus 1 times xy? Well, we multiply the first row with, we do the dot product, as we will see, with xy. So we get 1 times x plus 0 times y. We get x. X times 0 plus minus 1 times y. We get minus 1. That's exactly what we wanted, isn't it? So this matrix actually induces the transformation, which is the reflection on the x-axis. So another way of computing the effect of t on a vector is to multiply that vector by this matrix. Isn't it cool? It is. People are saying it's so cool. I mean, absolutely. We are going to tell our boyfriends afterwards. And so should you, especially if you want them to leave you immediately. But anyway, it doesn't really matter. This would be called a transformation. Transformation in your life for good or for worse. Okay? Don't tell my wife. Okay? Anyway, shall we see another example? Why not? Your colleagues didn't answer, but I'm answering for them. What else we did? Okay, there is one thing that we did. Remember the fattening of the axis? Let's double the x and let's leave the y's unchanged. That's one of the things we saw before. So my question to you is there a matrix that induces this transformation? Your colleagues here are saying yes. So let's see. What would be the matrix A that could possibly induce this transformation? Now, we want to double the x component. So what is it that we want to put here? A 2. Okay? And what is it that you think we should put down there? A 0. Okay? And we want to leave the y unchanged, isn't it? Okay, so the best way to leave it unchanged is to have the same effect as the identity matrix. And at the moment, this might look like magic, but in fact, there is an algorithm for generating these matrices when they exist. So let's check this out. What is 2001 times xy? Okay, 2 times x plus 0 times y, that's 2x. 0 times x plus 1 times y, that's y. Bingo! This matrix actually induces the transformation that doubles the size of x and leaves y unchanged. Yes? Okay, the question is, doesn't matter what we put here. Is that what you were asking for? Yeah, okay, so let's assume that we put something else there. So let's say we put some number A, and we do the multiplication. Okay, so we get 2x here. That's okay. But otherwise, we get A times x plus y. This is kind of like a y shear in the second component. That's what we're looking at. Remember this x shear when we were tilting? But now we are tilting, but with respect to y. While at the same time, we are doubling the size of x. So per se, this doesn't work in general. It only works, well, at least for this transformation that we wanted to achieve. It only does it when a is 0. A must be 0 in order to get what we want. However, this is a reasonable transformation. It just does, in general, something a little different. One more example. Suppose that I now want a transformation that does this. Okay, give me a vector xy. I add 1 to x, and I turn the y to 0. So I project on the x-axis. So what does this do? Let's look at an example. So, and let's... So if I apply this transformation here, where does the point 0, 0 go? The point 0, 0 goes to 1, 0. So this goes to this, because we're increasing the x component by 1, and we map the y to 0. It was 0. How about the point 0, 1? Where does this go? This point here. Some people are saying 1, 1, but if you look at the y coordinate, it always becomes 0. So where does it go? To the same. This goes there. And how about the point 1, 1? Where does it go? Okay, it goes here. And how about the point 1, 0? 2, 2, 0, 2. Okay, we are projecting, by turning the y into 0, we are projecting on the x-axis, and we add 1 to the x component. Now, my question to you is, do you think there is a matrix that implements this transformation? Okay, we could do some calculations to figure that out and see whether that's possible. So what is the property that this matrix should have? Okay, so, well, it has to be 2 by 2, isn't it? And moreover, when we multiply it for xy, what is it that we get? So this should actually be equal to x plus 1, 0. So what is it that we would get? Okay, so we have a times x plus b times y And here we would need to have c times x plus d times y. So this thing here should be always equal to x plus 1. Is it possible? Well, this should always be equal to x plus 1, no matter what x is. Now, x is a parameter. So you have to find a and b such that a times x plus b times y, and those should be fixed, should always give you x plus 1 afterwards, no matter what x and y you put in. Well, if it were possible, that sort of looks nearly like a miracle. And we all know that, unfortunately, miracles don't have a knack of appearing too often in our lives, unless we have epiphanies. Sometimes they may happen, but they happen once if they happen, if you're lucky. Okay, so in fact, it turns out that there is no matrix that can induce this transformation. What we're going to do now is to figure out how we can actually scientifically, and not by guess, by doing a lot of work, figure out when a transformation from vectors to vectors can be implemented in terms of matrix multiplication. To do so, we will characterize a collection of functions which are really, really nice. Now, what do I mean by really, really nice? I mean that they look like this. They are functions that we call linear. Now, when is a function linear? The function is linear if it has these two fantastic properties. And what are these two fantastic properties? Well, the function interacts very nicely with respect to two operations that you all know and love: addition of vectors and multiplication of a vector by a real number. What does this mean? Well, in order for a function to be linear, it has to be the case that if you feed it with the vector x plus y, you can compute the value recursively. You thought you'd forgotten about recursion? Well, you haven't. There it is. If you want to compute t applied to x plus y, you compute the value of t fed with x, the value of t fed with y, and you sum the results. That's not always true. But if it is, it's beautiful. The function has a chance of being linear. Why do I say has a chance of being linear? Because there is something else that the linear function satisfies. If you feed it with a vector that is a times, where a is some real number, the vector x, then to compute the result, you compute the value of t applied to x and you multiply the result by a. So these are two properties. And they may not look like very much to you, but they mean a lot. Why? Let me get you really interested. Now, we studied the cardinality of real numbers. Are they countable or uncountable? Uncountable, resounding answer from the crowd. There are a hell of a lot of those, uncountably many. So pairs of real numbers, they are also uncountably many. There are a hell of a lot of those. But suppose somebody tells you, here's a function t that takes pairs of real numbers to pairs of real numbers. And that person tells you that function t is linear. You know what? If you know what t does to two vectors, you will know what it does everywhere. Isn't that nice? It's not like sort of a function like, I don't know, e of x or logarithm of x or whatever your favorite function is. Those functions don't have this property that if you know what they do to one real number, you will know what they do to every real number. But for linear functions, that's true. Even though they act on uncountably many things, they are very finite. They are determined by what they do on a very small number of vectors. That's why computer scientists love them, because we are not uncountable. We are not even countably infinite. We love finite stuff. We love it. And as it turns out, actually, finite is much more difficult than infinite. And in the rest of your careers as computer scientists, you will see lots of theorems that prove, actually, that what I'm saying is not unfounded, it's actually proven. Finite is much more complicated than infinite in many situations. So let's look at some of the examples that we had before. In particular, the last one. The one where I claimed, well, this guy here perhaps is not induced by a matrix. In fact, it is not induced by a matrix. But is it linear? Let's see. In order to argue whether this function is linear, what we would want to argue is that it satisfies both of the properties that we had before. If I apply t to a sum of two vectors, the result is the sum of t applied to the two vectors. If I apply t to the multiple of a vector, the result is apply t to the vector and then multiply it. Is this true? Well, let's see. So for instance, if I apply this function t to, let's say, the vector 2 times one zero. What is this? Well, this is t applied to the vector 2, 0, because 2 times the vector 1, 0 is I multiply every entry by 2. And what is this? Okay, x is 2, so x plus 1 is 3. And this will be 0. Now, is there any chance that this is going to be equal to 2 times t of 1, 0? Even without calculating what t of 1, 0 is. Is 3 an odd number or an even number? I think last time we looked at it, 3 was odd, and it hasn't changed since then. But if I have 2 times something, I'm going to get a vector whose components are all even. So that's not true. This cannot be. This thing is not linear. This thing is not linear. In fact, we could also do the calculation. T of 1, 0 is 2, 0. We multiply it by 2, we get 4, 0, not 3, 0. So this is not linear. Perhaps there's something there. Perhaps there is a connection between linear functions and functions which are induced by matrices. Perhaps, in fact, there is. We will see next time round that the two are the same, one and the same. linear functions are exactly the functions that can be induced by matrices. And just before we break, let me show you some consequences of the definition of linearity. Suppose somebody tells you t is a linear function. What is the value that t will return when you feed it with the zero vector? What do you think? Somebody said 0, and that's absolutely right. Why? Because the zero vector you can obtain by taking 0 times any vector that you like. So t of the zero vector will be equal to 0 times t of whatever vector you like. But 0 times any vector you like is going to be 0 anyway, the zero vector. So a linear function always maps the zero vector to a zero vector. And this immediately tells you that a function that does txy equals x plus 1y cannot be linear. Why? Because it maps the zero vector to 1, 0. What we'll see next time round is that there are lots of other nice properties of these functions. Any questions before we stop at 13:55? Okay, so I know you can't wait for Thursday where you will see all the rest about linear functions. In the meantime, be linear.